All right, continuing on with chapter 9, we've talked about how we use Lewis structures and then apply VSEPR theory to those Lewis structures to determine geometries or shapes. And we talked about two different types of geometries, electron domain geometries, which include both the bonding and non-bonding pair, and also the molecular geometries, which focus on just the bonding domains. So this section 9.2, what we're going to do is combine geometry with bond polarity in chapter 8 to determine molecular polarity. So I find that's where students start to be confused. There's bond polarity and there's molecular polarity. Bond polarity was discussed in chapter 8. We looked at the electronegativity difference between two elements that were bonded together, and we determined that if the electronegativity difference was between 0 and 0.4, we called that a polar or a non-polar bond, or a pure covalent bond, or just covalent bond. If it was greater than 0.4 but less than 2.1, we called that a polar covalent bond. That meant that the bond had a positive end, a partially positive end, and a partially negative end. And then if the electronegativity difference between the two elements was that were being bonded together was 2.1 or greater, we called that an ionic bond. So we're not talking about ionic bonds in this chapter. We're focused only on covalent or polar covalent bonds. So we're going to apply bond polarity to the three-dimensional geometry. We're going to do vector analysis. I'll show you what that means. And then we'll determine molecular polarity. And this is really important because molecular polarity we see on the macroscopic level in terms of melting points, boiling points, surface tension, vapor pressure. So all of those things are related to the intermolecular forces, the forces between molecules, and what gives rise to those intermolecular forces is geometries and molecular polarities. All right, the next slide. What we have here is a common Lewis structure we've done multiple times, and that's carbon dioxide. So carbon dioxide, black stands for carbon, red stands for oxygen. They have a Lewis structure there, or they have actually just have a shape of a carbon dioxide. It doesn't show the non-bonding pairs on the oxygens. But what you see here is, first of all, we would evaluate the type of bond that is occurring between carbon and oxygen. And so you would say that the electronegativity of oxygen is 3.5, and the electronegativity of carbon is 2.5 for a difference of 1.0. And you'd say, oh yeah, that's a polar covalent bond. And that it has direction, which they show here. And it has direction, which we show here. So that's bond polarity. Now, we're going to take into account bond polarity with what we've learned in chapter 9, and that is, what is the classification for this molecule? Well, it would be AX2. There are no, you're looking at just the carbon in the center. A stands for carbon, and the X stands for the bonding groups coming off of the carbon. There's two. Remember, VSEPR does not distinguish between a single bond, a double bond, or a triple bond. So This X2 represents two bonding groups coming off. And then I'd ask you, how do you keep two things as far away from each other as possible? And you'd say, yeah, they're 180 degrees from each other, like so. So this molecule has an electron domain geometry and a molecular geometry of linear. So these forces, this dipole moment that is created by the bond polarity for each bond is equal and opposite in force, and they cancel each other out. So when we add the force moving to the left to the force moving to the right, they exactly cancel each other out, and so therefore the summation equals 0. That's what the sigma stands for here, summation. And so this is along the x-axis, so that's why the summation along the x-axis is 0. There is nothing on the y-axis, so definitely the summation along the y-axis is 0. So you go, why do I need to know this? Well, what we've done here now is we've taken the Lewis structure from Chapter 8. We've determined the bond polarity from Chapter 8 using the electronegativity differences. We have applied VSEPR to determine the three-dimensional geometry of carbon dioxide. We've applied the forces of the bond polarity, and graphically we see that, or visually we see that as these arrows going equal and opposite, and they cancel each other out, so we know that carbon dioxide is a nonpolar molecule. And you go, well, why do I need to know that carbon dioxide is a nonpolar molecule? Well, we're going to find out that water is polar, carbon dioxide is nonpolar, so nonpolar substances do not dissolve in polar substances very well. And so we don't expect carbon dioxide to dissolve in water. We expect it to bubble out. So what you notice is in your day-to-day life is you get a Coke or a Pepsi or maybe a Sprite, and you look at a Sprite and it's a clear, colorless liquid, and then when you remove the cap and the pressure, all of a sudden the carbon dioxide bubbles start coming out of the solution, and you say, well, that's a carbonated drink, or that's a live water, but the carbon dioxide doesn't dissolve appreciably at room temperature and normal atmospheric pressure. And so when you release the pressure under the cap and it's room temperature, you definitely see a lot of fizzing. So that's where we're going with this. Is ultimately what we're trying to find is things like surface tension, boiling point, melting point, and dissolvability, solubility within a solution. All right, so let's look at another one here. The next one, we're looking at something like, they give us an example of what this one is. Chlorine, I'm going to say nitrogen trichloride. Is that right? Let's see. Let's think about this for a second. That's NCl3. This is 5 plus 3 times 7. So we're looking at a 26 electron system. And we know that there's 8 here. That's 8 here. That's not what this is. This is something else. Yeah, these are chlorines. These are chlorines. All right, just to make this work, we'll call it boron trichloride. Boron trichloride. All right, so if this is boron trichloride and the electronegativity of boron, let's just say it's 2.0. I'm just guessing it's somewhere around that. And then chlorine is 3.0 for a difference of 1.0. So we've determined the 1.0, 1.0. So we are the electronegativity difference is 1.0 for each one of these bonds. So we do have polar covalent bonds, and the geometry, since it's boron trichloride, I say it's boron trichloride, we get AX3, and AX3 lends itself to an electron domain geometry and a molecular geometry of trigonal planar. So we learned that from section 1, that this geometry is trigonal planar. So we have forces going out to the more electronegative chlorines. And the question is when you look at this as a whole, is there an overall direction these arrows are pointing? And hopefully you say no, that these three arrows are not pointing in any particular direction. Now, if you've had vector analysis before, what we need to do is we need to figure out how much of this force, when transposed to the y-axis and pointing this direction, how much of this force translates to being on the y-axis. So if you've had some geometry, you'd say the cosine of 60 degrees, which is a half. So half of this force is going from here over to here. And the same thing here. And so those two half forces add up to be a full force that cancels out with this force. And so the overall summation of which forces on the y-axis is 0. So that's what happens here. And so you're going, oh, I don't remember how to do this. I'm lost. Well, it's okay if you can at least look at that and say which direction are these arrows pointing overall, and you say they're not pointing in any one particular direction overall, then the forces cancel each other out. But if you can do it by saying the cosine, let's say this force was 5, so this would be the cosine of 60 times 5 and the cosine of 60 times 5 for the other one, and what you'd get is this would be 2.5, this would be 2.5. When you add those together, it's 5 in the opposite direction of this 5, and they cancel each other out. And so what you say is this molecule, the molecule is nonpolar. And it has no dipole moment. So no dipole moment on the molecular scale, and the molecule is nonpolar. So again, this substance wouldn't dissolve in water very easily. So that's what we're looking at. That's the kind of thing that we're doing in section 2, is to be able to, again, take Lewis structure plus electronegativity from chapter 8, apply VSEPR to it, and determine whether the molecule itself is polar or nonpolar. Again, molecular polarity, chapter 9, bond polarity, chapter 8. So our next example is water. And so water, water is, Lewis structure. Let's do that. You guys have done the Lewis structure, I'm sure, plenty of times for water. And so it looks like this. A lone pair here and a lone pair here, and you know that it's AX2E2, and you know that the electron domain geometry is tetrahedral. Tetrahedral means four-sided, but the molecular geometry is what you see with the bonding groups only, and you'd say, oh yeah, that's bent or angular. So here, people that haven't had VSEPR, they think water's linear. They think it's a line. And it's not. Again, when we apply VSEPR to it, we determine that it's 4 things coming off the central atom, and it takes a tetrahedral framework, and then we end up with a bent geometry. Now, you know that oxygen is 3.5 for the electronegativities, and these are 1.0 for a difference of 2.5. Oops, not 1.1. What am I doing? This is 2.1. This is 2.1. I don't know what I was thinking there. All right, so 3.5 minus 2.1 is 1.4. That's more like it. 1.4. And we know 1.4 is a polar covalent bond. The difference in electronegativity is 1.4, and the bond then is polar covalent. So unequal sharing of the electrons. Electrons are being pulled towards the oxygen. And if you look at those two vectors, you know that the overall vector resultant force is in this direction. All right? So when you add the two arrows together, think of it that way. If you add the two arrows together, the overall force is in an upward direction. This is called the resultant force or vector. And now that you have an overall force going in an upward direction, you have a positive end to the molecule and a negative end to the molecule. So this molecule has a dipole moment, and because it has a dipole moment, we say the molecule is polar. Not just the bond, the molecule. So the only way we can determine polarity of a molecule is if we know the geometry and we know the types of bonds, the bond polarities of that substance. So again, don't confuse bond polarity and molecular polarity. In order to get molecular polarity, you have to know bond polarity, and you also have to know the correct geometry. So again, what happens here, if you do the cosine of this angle and the cosine of this angle, overall there is a force going up in this direction. That's the resultant force. That's why they say the summation is not equal to 0. It's greater than 0. And so therefore this molecule is polar. All right, next one. So next one we have carbon tetrachloride, and this is a classic example of why you can't just go by Lewis structure and bond polarity. Because if you did the Lewis structure for carbon tetrachloride, here's the formula for it. You would say, oh, it's carbon in the center, it's a chlorine here, it's a chlorine here, it's a chlorine here, and it's a chlorine here. And then you'd have, I want to cheat here. This is how you cheat. Each one of these lines represents a lone pair. So that's how you quickly get through this, although you wouldn't represent it that way, on your homework or an exam. So you'd use dots, right? And so you look at this and you go, looks like it's square planar. It's 90 degrees here. Well, we know that's not the case. We know that the classification according to VSEPR is AX4, and the way you keep four things as far away from each other as possible is you arrange them in this geometry, which is called tetrahedral. And you can see that angle right there is greater than 90. It's 109.5 degrees. So all these angles here, all angles between chlorine and green, carbon and black, chlorine and green, equals 109.5 degrees. All right, so then you evaluate the bond between carbon with an electronegativity of 2.1 and the chlorine, which is 3.0, for a difference of 0.9. And you go, oh yeah, 0.9, that's a polar covalent bond. So we do have bond polarity, but when we look at all these vectors, can you tell me one direction all these vectors are pointing? And you would say, no, they're all going their opposite way. And so if I, again, transpose all these forces onto the y-axis, doing the angle between the vector and the y-axis, they actually all cancel each other out. And this is a non-polar molecule. It means it will not dissolve in water. Water's polar. Carbon tetrachloride's nonpolar. And you go, why do I need to know this? Well, carbon tetrachloride at one time was used as a dry cleaning agent. It would clean wool very well. You know, if you add water to wool, it pills up, it shrinks, it really damages the wool. But you could take your wool, clothes to the dry cleaner, and that's what a dry cleaner does. They don't use water, they use other nonpolar solvents to dissolve the nonpolar greases and oils out of your clothes, and they're clean, and so it doesn't damage the wool. So carbon tetrachloride was like one of the best dry cleaning agents, but they found out in the late 60s, early 70s that it's carcinogenic, so we don't use it for dry cleaning agent anymore. But it was a great dry cleaning agent. In fact, carbon dioxide in some places is used as a dry cleaning agent. Again, nonpolar, and they make a supercritical fluid out of it. A supercritical fluid is one that it's not a liquid or a gas. And so I don't think we get to really talk about supercritical fluids in Chem 170, but it's used as a dry cleaning agent in some places. It's a pretty expensive dry cleaning process, though. All right, so then they want you to look at this one, because this one's important too. So this shows you what happens when one of the chlorines is substituted and the hydrogen's placed here. So you know the difference in electronegativity between the carbon and the chlorine is equal to 2.5 minus, I did this wrong up here. This was 2.5. So a difference of 0.5 up here. Let's see, 2.5 and 3. Yeah, the difference up here was 0.5. Yeah, this is 2.5. I said 2.1, it's 2.5. This is 2.1, so a difference of 0.4. So we would say that's just a pure covalent bond. And then 2.5 out here to 3.0 is 0.5, so this is a greater force pulling out this way. So overall, these three carbon-chlorine bonds dominate the force of the between the carbon and the hydrogen, and so the overall resultant force is in a downward direction. So this force here, even if we look at it, it actually is a downward direction too, because carbon is more electronegative than hydrogen. So that's what this is. But the overall resultant force is in a downward direction like that. Actually, they should have drawn it like that. So because the overall force is pointing in a downward direction, called the resultant vector, this substance is polar. So just knocking off one of the chlorines and putting a hydrogen, we go from a nonpolar substance to a polar substance. I mean, that's what's so wild about this. It's just one change, one element changed in the bonding scheme, and you go from nonpolar to polar. So this substance dissolves in water, this substance does not. All right, this is one that's really big when we talk about organic chemistry. It's called the cis and trans isomer. So I want you to make sure you understand what this means here. Structural isomers. They must have the same chemical formula but different arrangements. That's what a structural isomer is. Same chemical formula. This is C2H2Cl2. Same chemical formula, different arrangements, and one is polar and one is nonpolar. So in this one, here's the chlorine, and then across, if you go across here, here's the other chlorine. So across is called trans. All right. And beside, where the chlorines are on both sides of this of the carbon double bond, this is called cis. So we have cis and trans. So you can see if you add these vectors, this vector and this vector are equal in force. The difference is 3.0 here, 2.5 for the carbon. Same thing here, 2.5 for this carbon and 3.0 for the electronegativity of the chlorine. So those forces cancel each other out, and these forces cancel each other out. They're going opposite, they're going towards each other, they cancel each other out. And so overall, this is a nonpolar molecule, nonpolar. So this substance does not dissolve in water. Whereas when both of the chlorines are on one side, the forces are all, the resultant vector is in a downward direction. These are down, and overall the resultant vector is in a downward direction. And so if it's in a downward direction, the summation of the forces is not zero, and this becomes polar. So what's neat about this is you can dissolve substances in these compounds. If it's polar, it's going to dissolve in this substance. If it's nonpolar, it will dissolve in this substance. So you can actually separate polar and nonpolar substances. The polar will dissolve in the trans, and the nonpolar substance will dissolve in the cis. So cis and trans, these are called structural isomers. Same chemical formula, different arrangement of atoms gives us different molecular polarities and different melting points, boiling points, surface tensions, vapor pressures, and so forth. That's what we're going to be talking about in chapter 11. So you must master section 9.2 in order to understand chapter 11. All right, that's it for section 9.2. 9.3, this is real easy. I'm not going to spend a lot of time with this, but when we talk about bonding, so let's just look at this. We know that the S orbital looks like this. So we got the 1s, we got the 2s, and then we have the directional characteristic of the 2p. And the 2p goes out along these axes like this. So in section 3, it's called valence bond theory. And valence bond theory says that atoms that are bonding together, they overlap just a little bit over, like so. They don't overlap a lot because the nucleus of this atom, let's change the color here. Let's see if we can do that here. Oh, I can do it up here, yeah. Let's see, I need a black maybe. So there's the nucleus of this atom and the nucleus of this atom, and the nuclei repel each other. There's big positive charges here. Now, the electrons of this atom are attracted to this nucleus, and the electrons of this atom are attracted to that nucleus, and the sharing of the electrons creates a bond. But there's minimal overlap that occurs between the atoms. And so it is the valence bond. Valence bond. The valence shell electrons bond to the other atom or element to create a polar covalent or covalent bond. So that's what they mean by representing electrons in the orbital diagram, and also energetics and directionality of the bonding. Because P has direction to it, S does not. All right, so according to valence bond theory, when an atomic orbital on one atom overlaps with an atomic orbital on the other, each overlapping atomic orbital must contain a single unpaired electron. Makes sense, right? Each one has its own single electron, and they bond. When they bond, they must have opposite spins because an orbital can only hold 2 electrons. Now, again, what determines that you can't just overlap them 100% is the nuclei are attracted to the electrons, but the nuclei are repelled from each other. So there's some optimal overlap that occurs between the atoms. So this represents, you know, that hydrogen, we know it is, it's hydrogen. It's got one valence electron. It shares its electron with the other hydrogen because they both have the same Z effective, so they can't strip electrons off each other. And there's an optimum overlap that occurs between the 2 hydrogen atoms. And you say, where is that optimum overlap? Well, the optimum overlap occurs at the lowest energy. which we call an energy well. So the lowest part of the energy, called an energy well, is how we determine optimum overlap. And that can happen with S or P or S and P. So here's some examples of that. So we have like two hydrogen atoms overlapping here. All right. Here we could have, let's say, carbon and another carbon overlapping, the p orbitals of the 2p overlapping here. And then we could have a hydrogen overlapping with the p orbital of a carbon here. All right, so there's SS overlaps, there's PP overlaps, there's SP overlaps, and these can get really complex, but these are the basic ones that we've seen already using the quantum mechanical model that we learned in chapter 6, and knowing p orbitals have direction, s are unidirectional. This is what this would look like. Here we get something a little fancier. We can see that like when two fluorines overlap. So two fluorines overlap. Here's the orbital diagram of fluorine in the valence shell. That's what it looks like. Fluorine would like to have another electron here to have a full outer shell of 8. How does it do that? It shares the fluorine. This fluorine shares its electron with this fluorine, so each fluorine feels like it has a full outer shell. And here we get a P to P overlap. So P to P overlap, and it's directional. It is in this case, the z-axis P of each one that creates the bond there. And then we could have something like hydrogen fluorine. Oops. And again, there shows an S and P overlap. And again, notice the hydrogen doesn't just plant itself like here. What repels these two things are the nuclei, but there is an optimal overlap here. How much overlap occurs determines where the lowest energy point is. As those start to meld together, there's this drop in energy. And that when that energy drops to a minimum, which we call an energy well, that's optimum overlap. So this is what I've been saying. This is what we would graph. If we graph this, we see that in the case of two hydrogens, here are two hydrogens acting independently, and they have a baseline energy of this. As the hydrogens start to overlap, the electrons of this atom are attracted to the nucleus of that atom, and the electrons of this atom are attracted to the nucleus of that atom. At some point we get optimal overlap, and that's at the lowest energy here, negative 436 kilojoules per mole of energy could be released, and we're at the bottom of the energy well, optimum overlap. Now, if we try to overlap these more and more, the energy goes through the roof. See how steep this is? And it does. It literally goes through the roof. You go, well, why do I need to know about this? When you've been talking about the last couple of weeks in the news, they've been talking about nuclear fusion. That's what you're trying to do. If you could actually take a hydrogen and fuse it to another hydrogen, it would become helium. And the difference in mass there would release large amounts of energy when we start talking about Avogadro's number of atoms or more. And we get lots of energy, and we don't get the radiation byproduct that we have with nuclear fission, which is what we use today. Today what we do is we split the atom into, and then it gets to be a chain reaction, but we split the atom, and the problem with that is the products left over can be highly radioactive for many years. They may have very long half-lives. But fusion, just taking two hydrogen and bonding them together to form a helium, that's the holy grail of energy. And when they're just really, getting to the point where it seems like it's going to be successful, we're still 5 to 10 years out. But if fusion really takes off, it looks to be like an almost unlimited energy source. So we won't be worrying about fossil fuels or radioactive fission. It's got real big potential. Like I was reading something the other day. It said if fusion takes off, we'll start seeing buildings made out of different materials that are that cost a lot of energy to make. Like you could make a building out of titanium because you have so much energy, unlimited supply of energy. You can start, purifying titanium and then using it as a construction material. Right now, it's way too expensive, but if energy is one of the big costs for it. But if energy is not a problem, then materials start to really exotic materials seem common then. So here, what I want to show is that, and the reason why they're doing this, they just want to show something which is really important to think about. So if this hydrogen bonds with the p orbital and this hydrogen bonds with this p orbital, you would expect the angle here to be about 90 degrees, right? 90 degrees. Now, it actually comes up to be 92. The sulfur is in the middle, and then the hydrogen is attached here and here. And that's pretty close. I mean, you got some electron repulsion here, but you also have a little bit of pushback here, but it is 92. It's 92 degrees. So some electron repulsion here makes this angle open up, overcomes this, and then we get a little bit of opening, 92 degrees. And you go, well, that's pretty good. Look, it predicts that pretty well. 90 degrees, we get 92, not so bad. And again, what happens is sulfur, one hydrogen's electron goes here, one electron goes here, sulfur is satisfied with 8 in its outer shell, and each hydrogen is satisfied with 2 in its outer shell. So it works really well. Now, you're looking at this and going, well, what about water? You told me water looks like this, and we know that the angle we've memorized, it's 104.5 degrees. What happened to 92? Because you would expect oxygen and sulfur, they're in the same group, so why isn't water 92? Why is water not 92 degrees? So this is the problem. We know this is the fact. We've measured it. We know it's this. We would expect it to be 90, or at least this similar to hydrogen sulfide, and it's not. So what's going on? So we find out that this valence bond theory, it's simple, but it doesn't explain everything. So the bottom line, valence bond theory says that bonds form when singly occupied atomic orbitals, that means orbitals that have one electron only, share their electrons and with opposite spins, and there's an optimal overlap where the potential energy is at its lowest. And we call that the valence bond theory. Problem is, it doesn't work with many of the covalent compounds that we've been talking about. Worked for hydrogen sulfide, definitely does not work for oxygen. So to give you an example here, so hydrogen selenide, foul smelling gas. Here's what selenium looks like. Looks a lot like sulfur. It's just that it's in the four shell instead of the third shell. And so there's two bonding sites. We would expect the hydrogens to bond in there, each electron to form that, and that's what we expect. So let's go back, and we already know what this looks like. It looks just like hydrogen sulfide, H2S, right? So electron of hydrogen goes there, electron of hydrogen goes there. We get a nice overlap. And the degree, about 92 degrees. Well, it should be the same as this. These are in the same group. But again, we haven't explained what's going on with water, which is in the same group. So we need new theory. So, section 4, which is the last section we're covering in chapter 9. Oops. Let's see, I messed up there. I didn't show you that. I've been talking about it. My slides are not working independently. I mean, they're working independently. They're not connected. So that's a problem here. So let me go back. So again, what I was saying here is the hydrogen sulfide, hydrogen selenide, we'd expect it to be like the hydrogen sulfide. Here's where the one electron of hydrogen goes. Here's where the other one electron of hydrogen goes. And again, hydrogen sulfide, hydrogen selenide both have a approximately 92-degree angle between the hydrogen, the sulfur, and the hydrogen, 92 degrees. But we know this one's 104.5, so something's not working right. Something's not quite working here. So that brings us to the new theory called hybridization. Those of you planning to take organic chemistry, you will really want to spend the time on this because most of your organic chemistry is hybridization. It's hybrid orbitals. It is not valence bond theory orbitals, it's hybrid orbitals. So what we're going to do here is we're going to blend the s orbital with p orbitals and maybe d orbitals and create a new set of hybridized orbitals. So let me show you how this works. So we take a s orbital, which is spherical in probability, all right? And we combine that with a p, and we get these orbitals called sp orbitals. So sp orbitals, notice they have large areas for bonding. And where do we see sp orbitals? When we see something that's AX2, that's linear, like carbon dioxide or beryllium. So here's what's going on here. Beryllium only has two. It had two electrons, right? It was 2s. So what happens is the 2s electron jumps up into the 2p, or we combine it with the 2p. I don't want to say jumps up. I want to say we are applying a new theory and we just take the electron out of the 2s and put it in the 2p. And you go, why would you do that? Well, now you have two orbitals that have the same energy. Remember, the p is normally a little bit higher than the s. We learned that already. But what if I take one of these p's and one of these s's and I get a sp and a sp, and they have the same energy? And each one has one valence electron. Well, that would allow a chlorine's electron to come in here and a chlorine's electron to come in here, and that's how we would bond beryllium chloride. And you kept saying, well, why doesn't beryllium follow the octet rule? Or here it is. By taking the 2s electrons in beryllium and moving one into the p, we have two bonding sites now called sp hybridization, and we get two bonding sites, one for each chlorine, and we get a linear geometry. So sp is associated with a classification of AX2. All right, so let's look at another one here. And that's actually, it is the beryllium chloride. So here's what beryllium looks like. It has, remember, it's 1s2, 2s2, and then it has nothing in the 2p. But the p are there, and they do have direction to them. So by taking the s and the p and getting two sp orbitals, hybridized orbitals, that's what the green represents here. Then we have the ability to accept an electron from the chlorine, and this one has the ability to accept an electron from the chlorine, and we form this substance here. The only thing is, this is the problem with this. There's a little bit of incongruity here. So this is what the sp hybridized looks like. It doesn't look like a p. It looks it looks much larger. I mean, it's not got that, you know, this and this. It's actually changed because the S and P have combined. So I don't know why. I think that was a mistake that they actually show it this way. All right. Or you could argue that it isn't hybridized, but we know it's a P overlap. It's similar to a P overlap. Otherwise, it would be somehow an S and P overlap, and it's just not that. So that's the problem. That's why we use hybridization to explain geometries that just don't come out of our normal thinking of geometries. All right, especially when we say bonding occurs when atoms have unpaired electrons. So here's an example of boron, maybe boron trifluoride, something like that. So this is what boron's valence orbital diagram looks like. So only one thing should bond with boron. Only one thing should bond with boron. But what if I take this electron and put it over here and I get this? Now I got 3 bonding sites. And now we learn why boron doesn't follow the octet rule. It is going to be satisfied with 3 bonding sites. So an F goes here, an F goes there, and an F goes there, and we get boron trifluoride. So we've taken an S, we've blended with it 2 P orbitals, 2 P, just one orbital, 2 P orbitals. And we get 3 hybridized orbitals, and then you know that if it's 3 bonding sites, it's AX3, and you know that is trigonal planar. So this is, and see, this is the way it works because we know it's trigonal planar, and we know the angle is 120 degrees. Well, if it wasn't hybridized, remember the P are just along the axis 90 degrees from each other, so that's not working. So just looking at the orbitals that we've talked about in section 9.1, that doesn't work. The P's do not work. We know by experimental evidence that the angle is 120 degrees. So we've had to come up with a new theory, hybridization. So we've taken an S and 2 P's, and now we have 3 bonding sites, and the 3 bonding sites, to keep them as far away from each other as possible, is the corners of a triangle, and we say, oh, this is SP2 hybridization. So if it's SP2 hybridization, it's going to be trigonal planar. If it's just SP hybridization, you know it's going to be linear. So that's what I want you to get out of this section is based on why does it happen? It happens to give us bonding sites so that elements can bond together. And then it's related to geometry in that AX3, we need to have 3 bonding sites, and we know how do we keep 3 things as far away from each other as possible, corners of a triangle, and we get the electron domain and molecular geometry is SP3. All right, so this is what it looks like when we combine these together. They are, notice you've taken 2 P's, and you get the 120 degrees there. Now I got the smaller lobe, like this is the smaller lobe of this. This is the smaller lobe of this. This is the smaller lobe of that. And so, but we get a nice 120 degrees. Everybody likes it. And then something can bond here, something can bond here, and something can bond here. So this would be like boron trifluoride again. Boron here, fluorine here, fluorine here, fluorine here. And notice we said they're all about like single bonds because the length of all these bonds is the same. We know there's no double bond to give boron a full outer shell of 8. It's satisfied with 6. And so works out perfectly here. Works out perfectly. So hybridization of sp and d orbitals. Boron trifluoride, nonpolar molecule. Think about that. So there's our example. Works out perfectly. Now, you say, what's this white here? What is this white? Well, one of the P's wasn't hybridized, right? So this white one is an unhybridized P. There's nothing in it, but that's what they're showing the white there, unhybridized P. And it's staying along the, if you want to call that the z-axis or the y-axis or whatever, but it's staying along the same axis here, unhybridized. You're going to say that's X, and then up here through here's the Z, and then out through here somewhere is the X. Do that. Okay. So keep that in mind. One of the p orbitals is not hybridized. We just took two of the p, and then one of the, and then the s, and we can get sp2. Next one, sp3. sp3. All right. So we have carbon. Now here's the thing. If you look at carbon, you'd say it only bonds with two. It's only got two bonding sites. So how does it get four bonding sites? How do we get methane, CH4? Something has to happen. Well, this electron has to jump up into the P, and we combine the S with the P so that they're all the same energy, and we get four sp3 orbitals. All the same energy. Otherwise, it's the S's here, the P's up here. It doesn't make sense. Why would this want to jump up? Well, it takes energy to get that up there, right? But if I make them all the same energy, I take the 1s and I take the 3 and the 3 p's, and I combine those all together, I get four sp3 orbitals. So sp3, you know, this is AX4. There's four bonding sites here. 1, 2, 3, 4. And so AX4 tetrahedral, we know that. That's the electron domain and the molecular geometry. And again, if we didn't hybridize them, you'd think that, you know, everything would be 90 degrees from each other because the p orbitals are 90 degrees from each other. But we know that in a tetrahedral, that from this carbon out to this, and then we have let's say hydrogens like this. We know the angle is 109.5. Well, we can only get 109.5 degrees if we hybridize the orbitals. This does not, just looking at those atomic orbitals, unhybridized, we would get 90 degrees, and that's not what we get here. So again, hybridization, this theory, you say, why do we have hybridization theory? Remember what a theory is. It's a human construct. We use theories to help us explain and predict future events. And so by hybridizing these orbitals and saying they're all the same energy, we have now four bonding sites, and that's why carbon generally forms four bonds. And they all have the same energy, and it also explains why the angle is not 90 degrees, but 109.5 degrees. All right, so this is what they look like hybridized, sp3. So sp3, and you can see, yeah, there's the angle right there, 109.5 degrees. 109.5, 109.5, 109.5. We get a tetrahedral framework, one side, two sides, one back behind, and then one below here. Works out perfectly. And then they give us an example of methane, just like I chose. That's the most common one to use. And it works out nice. Again, you're not going to draw it like this. You're going to say, all right, carbon here, carbon in the same plane with the hydrogen, same plane with this hydrogen, this one going back through the board here, and this one coming out at you. Use a triangle for that. That's how you draw a three-dimensional object on two-dimensional space. Triangle means coming out of the board. All right, dash line means back behind the board. And solid line means in the same plane as the board or the screen. All right, they get even fancier. So you're saying, well, how do we get the how do we do phosphorus pentachloride? So phosphorus pentachloride, you know, it looks like this. Got the axial chlorines, then you got the equatorial chlorines. So you got 5 bonds coming off phosphorus. Well, if you look at phosphorus over here where it's not hybridized, it only has 3 bonding sites. But if I pop this one into the D, now I have 5 bonding sites. And that's what we said. In order for us to have an expanded octet, we have to have an unfilled D sublevel. And you say, well, why would it do that? Because D is higher in energy than the 3s or the 3p. But if I blend these and make 5 orbitals, 1, 2, 3, 4, 5, and they all have the same energy, they're all degenerate, sp3d, they all have the same energy, then each one has the same probability of being occupied. And so if we have AX5 for our categorization, then we know that it's trigonal bipyramidal. Trigonal bipyramidal. All right, there it is. Classic example, phosphorus pentachloride. All right, let's do another one. Last one, octahedral, right? Octahedral. So here we have, let's see, what do we want to do octahedral? I would say the common example here is sulfur hexafluoride. That's what I'm going to use as my guess. All right, sulfur hexafluoride. It looks like this. There's a fluorine. There's a fluorine. There's a fluorine coming out here. Actually, this one should be dashed. Dashed like this, fluorine. One coming out like that. One going down like that. And then we know there's 3 lone pairs on each fluorine. I'm cheating here by just using lines. All right, so let's just make sure this is right. 6 plus 6 times 7 equals 48 electrons, and there's 8 around each one of these, so that's 48. All right, so sulfur has 6 things bonded to it. We know it's an expanded octet. How does it do that? Here's what sulfur looks like. It only has 2 bonding sites before it's hybridized. And so I have to take one of these S and put it over here, and one of these P's and put it over here, and now I have S, all 3 p orbitals and 2 d orbitals. All right, I have the S orbital, 3 p orbitals, and 2 d orbitals, and so the hybridization is sp3d2. And now I have 6 degenerate sites. They all have the same energy. So we can have 6 things bond in here equally. sp3d2, so we know if it's AX6, it's called octahedral for the electron domain and the molecular geometry. That's how we get it. sp3d2. Hybridization has to occur here for this to work out. So there's what it looks like. Taking the S, the sulfur, we've combined 6 fluorines to it, SF6. So I don't know why they didn't do that. I would write that write the chemical formula here, SF6. All right. So in summary, this is what you have to memorize. All right. So if it's linear, it's sp. You have 2 electron domains, linear, AX2. If it's AX3, you have 3 electron domains, it's sp2, it's trigonal planar. And see, it works so great. The angles that we talked about in section 1 now make sense. And then if it's AX4, we get 1s and 3p orbitals. We combine those together, it's sp3. So anything that's tetrahedral is sp4. AX5, 5 electron domains, sp3d, trigonal bipyramidal. And AX6, 6 electron domains, sp3d2, octahedral. This is this is what you memorize. This is what you must. Everything up to this point in section 9.4 is to see the process, but when you go to apply it, what I'm going to be doing is this. I want to say, all right, I give you sulfur trioxide, and I want you to tell me what the hybridization for that is. So you go sulfur trioxide, okay, in chapter 8, I learned how to do a Lewis structure, so it was 6 plus 3 times 6. I'm dealing with 24 valence electrons. Sulfur is the least electronegative, so sulfur goes in the middle, and the oxygens. Now you don't know that they do that in chapter 8, but you know. But in chapter 9, you know that 24 electrons. What we're going to have here is something that looks like this. So let's do the Lewis structure. And again, I'm going to cheat. All right, there's my 24 electrons, 8 around everything. And you go, oh yeah, this has resonance. Double bond could be on this one or this one, but to save time, I'm not going to write all the resonance structures. So you'd look at this and you go, oh yeah, this is AX3. Well, if it's AX3, then it has to be sp2 hybridization here. And AX3 is trigonal planar. So you know the shape. And you know that it's hybridized because if it wasn't hybridized, it'd be like a p orbital this way and a p orbital this way and a p orbital that way. And it'd be more like 90 degrees. But it's not. It's 120 degrees. So that's how you know hybridization is taking place here. All right. Otherwise, it would be, yeah, oxygen here, sulfur here, double bond to the oxygen, single bond to this oxygen. So it'd be 90 degrees here. We know it's not that. We know it's this. Experimentally, we know it's that. So once you get the classification to make these angles work, you're going to have to tell me that it's sp2 hybridized. Otherwise, it doesn't work. You will not get the 120 degree angles there. If it's tetrahedral, like, again, methane, there's no way that you get 109.5 degrees here unless it's hybridized. Otherwise, these, the P's would be on one axis, and then you get 90 degrees where these attach like that. So we know that's not what's happening there. All right. I hope that helps. This is the main table. This is what you ultimately want to look at. And I will, here's just a summary of what you do. So draw the Lewis structure, count the number of electron domains. This is what I call classification here. So I call it classification. And so that's the most, I've said that over and over as we've done this. Like, say it's AX2E2, or make sure you get that classification. And then once you get it classified, you're going to do some hybridization to make the bond angles work. So draw a ground state orbital and then hybridize them so you have unpaired electrons, and then that'll tell you how many bonding sites you need. And then once you get all those bonding sites together, you'll find out that in order for it to have 3 bonding sites, it has to be sp2, 4 bonding sites sp3, 5 bonding sites sp3d, and 6 bonding sites sp3d2. If you do that, it'll be much easier. And I'll slide through this one. You can try it with ammonia here. So you know ammonia, it's got 3 bonding sites. And what tells you that it's hybridized, if it wasn't hybridized, the angle between the nitrogens and the hydrogens would be 90 degrees, but the actual angle is 107. All right. So that tells us that we're dealing with a hybridization. And we get something like that. So we get sp3, where the lone pair is when one of those hybridized orbitals. So hydrogens bond here and the lone pair is up in here somewhere. Okay, so there it is. The lone pair is one of the sp3s. That leaves us 3 bonding sites for each. So each hydrogen can go into that. So each site. So hydrogen here, hydrogen here, hydrogen here, and we get NH3. And the dead giveaway for this is the angle is not 90 degrees, it is 107. It's much larger than 90, and so that tells us that we've hybridized the orbitals. All right, that's where we'll stop. That's all you're required to know for Chem 170. If you are planning to take organic, you might want to look at these multiple bond ones as well. But for Chem 170, we're going to stop at hybridization of either sp, sp2, sp3, sp3d, or sp3d2 and the corresponding geometries. All right? Thank you.